lectures. So we were discussing about these growth mechanisms, kinetics, techniques, and effects of the oxide layer formation on the silicon die. We were talking about how this particular metallization and how these layout designs can be possible. We were discussing about different thicknesses. So if you can just see that different thicknesses will be useful for different application purposes. So accordingly, one has to have a very good control over the thicknesses in order to properly get a device that is required for our end outputs. Okay, so we were talking about these three important parts. So one is your front end processes, where we were discussing about the oxidation processes, deposition and oxidation processes. And in the back end, we will be having testing and packaging purposes. Uh, so we already discussed about this part. So we talked about what is thermal oxidation, how this thermal oxidation is useful for me to make silicon dioxide on silicon. And then we discussed why silicon dioxide is important in this particular process. So yeah, this is where we were discussing about the parts, like, okay, the passivation of the surface is important. You have some dangling bonds present on these particular surfaces. So if you try to cleavage the surface, you get these dangling bonds, and now you using these dangling bonds, one can have some masking on these particular layers. And using this, you can develop your different gates, drain, source, whatever you want, you can do that. Okay, so we talked about this particular process in the thermal oxidation processes. And in thermal oxidation processes, we discussed two important parts, or two important oxidation processes. One is the dry oxidation, the other one is the wet oxidation. And we were discussing about how these two oxidation are important for getting a controlled growth of silicon dioxide on silicon vapor. This particular growth kinetics was discussed by Deal Groove model. This is also we try to understand. There are linear and parabolic behaviors which were discussed by Deal and Groove models, and we try to understand this particular part here. So one can say that uh, the weight I mean the weight oxidation process is quite faster compared to the dry oxidation processes. There is also an intermediate oxidation process which is called as a radical, and that we have also discussed. So this is just the uh, a comparison about how wet and dry oxidation is been done, or the processes of wet and dry oxidation on the silicon surfaces or wafers is done, and which one is more effective. So depending on your uh, actual output that you're looking for, or the device thickness that you want, one can have either dry oxidation or wet oxidation processes. We talked about this particular part where we were discussing that how the reaction at the interface takes place. Thereby, there is diffusion processes that has also been occurred, which helps further to get the reaction and the diffusion processes to have an oxide layer on your surface. This is where we discussed about how the diffusion kinetics, or the surface reactions and the chemical reactions, are more useful, and along the distances of the silicon wafer, how these processes are important at different regions. Okay, so we talked about this very important part, why radical oxidation is important, because we already have wet oxidation, we have dry oxidation, but then why we require another radical oxidation. So we talked about that along the contours, whenever you have such kind of an sharp edges or a contour here, so in that particular case, if you try for a wet or the dry oxidation, then you don't get a proper or contour of your silicon dioxide throughout the edges of this particular silicon. But then if you go for the radical, then you get a very good oxidation layer that is been uh, conformally growth on these silicon surfaces or the edges of that silicon. So that is why we wanted to have this. This is the process where we call as an induction process, the diffusion limited process. So these are the two different processes when you try to have the oxidation on the silicon surface. So that we have discussed. This is how the wet and dry oxidation processes occur, and one can say that there is a radical, there is a linear or parabolic growths with respect to time for different wet or dry oxidation processes. The simplest equation that we try to understand for this particular purpose. Of course, this is not that simple. It's quite complicated, but we try to restrict ourselves for this simple equation to just understand that how this diffusion limited or the reaction rate limited growths of oxide layers takes place on the silicon wafers. Okay, so this is what we try to understand, that how one can get the source and gate in, or the other way I can say that how one can channelize to get different kinds of oxide regions present in the silicon wafer. Okay, so one can have a very good channel, an opening of a channel, and then one can very selectively grow this particular channel in between your silicon wafers. So that is how we were trying to understand, and accordingly one can go for this particular formations. So slowly we are moving into one by one part into how we can make a proper IC. I mean, how we can fabricate a proper IC using different techniques here. Okay. Okay, so we talked about this important part because, we are just explaining that how this oxidation is taking place, but by what methods, that is very important. So, different techniques we discussed, that is furnace oxidation, where we have horizontal and vertical furnaces that can be utilized for oxidation purposes. We talked about the rapid thermal oxidation processes, where you can have a very good control over different time periods. So particularly one can have a very fast ramp at the initial time, and then one can have a very good saturated portion where a controlled or a uniform oxidation growth can be taking place. Slowly one can either ramp the process downwards in time with respect to the temperature, or one can allow the system to cool naturally. So there are different parts that can be controlled through this RTO processes. So this is the furnace that we discussed about. So we have an horizontal furnace. This is the vertical furnace through which one can go for oxidation purposes. Okay, this is the actual process that takes place in fabs. So this is the furnace that we have shown here, and the oxidation is taking place. So you have this silicon wafer that is moving inside the chamber here. This is totally vacuum chamber, and then controlled gases are being inputted. These are the inert gases which just helps in the oxidation processes, and then at certain temperatures this oxidation process is occurred. So after oxidation, we already discussed that along the silicon wafer you can get a very good spectrum of colors, and depending on the spectrum of colors one can go and understand the thickness. I mean, uh, what thickness is grown on that silicon wafer, that can be understood to this particular chart here. Okay, moving forward you can, sorry, we just talked about this RTA or RTO method. So how the actual commercialization of this particular process took place, and when this RTA process was being utilized. Okay,
Sir,
we, yeah.
sir, your this presentation wasn't visible, sir. Only that notepad is visible, sir.
Oh, really?
Yes, sir.
Oh, okay, okay, okay. Sorry, sorry. I'll just make the corrections. Thank you, thank you. Oh, okay, 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 okay. Sorry for that. Now it's visible.
Yes, sir.
Yes, sir. Now it's
Yes,
visible,
yes.
sir.
Okay, okay, okay. Sorry, sorry, sorry for that. So thank you for correcting this. Okay, so we discussed about this part. So I'll just quickly move on further. so that will not waste our time. So yes, this is what the method look like and how you can have a controlled oxidation growth here. That is what we have discussed through the RTA methods here. Okay, this is the RTA. We have already discussed about this part. Why it is important, or one can say that how the RTA, I mean rapid thermal annealing process, is more uh, controllable or more useful compared to your conventional annealing processes that we have discussed. Okay, this is the actual process that takes place for a larger wafers. So we talked about this particular part, like how this growth is possible. So different steps of oxidation that takes place. We discussed about the silicon. Then we have a linear growth where we can have a very uniform oxide layer growth on the silicon wafer, and this can be quite thick. I mean, thick up to 500 angstrongs. Okay, we can have a parabolic growth where we can increase the thickness of the orders of 500 angstrom or more for this. We talked about this particular part, where what are the problems that are making, I mean, the different growth problems that were discussed by Deal and Group. So, and we were trying to understand that this particular part is very important, because when one is growing some oxide layers, so it is important to have a proper thickness, and because this thickness is later on useful for fabricating your different devices. So that's where one has to have a proper control, and to understand this controlling process, one also has to discuss about the problems, or whatever the problems they are going to face when they are going for such kind of an oxide layers. Okay, so this is what we have already discussed. So this is how it looks like. There is a transition region or a transition zone here. So when you have silicon, we have silicon dioxide that is growth on the silicon wafer, and along the interface one can see there is a transition zone where you have certain SiOx kind of an formation. So that is very important transition zone. Today we'll try to discuss this particular part here in details. What is this transition zone? We talked about polysilicon, and how this polysilicon is important, because whenever you are trying to fabricate such kind of capacitors or great electrodes, then it's important that you either go for a crystalline silicon, or else you can go for an polysilicon processes. Yeah, so this is what we discussed about, that how the surfaces, if at all there are some edges, say convex edges or concave edges at the corners, then how this can be controlled through the oxidation processes that we have discussed, and we have just seen this TM in images, which helps us to understand the oxidation process, which one is beneficial for us. Okay, we also talked about this, like how one can uh, fabricate a proper device. I mean, the channeling of this device is possible. That is what we have already discussed. Okay, we talked about the redistribution of dopants at the interface also. This is where we were discussing about that particular part, like in the transition processes, and you have a proper silicon dioxide interface, and beneath you have silicon wafer. So this total profile or the gradient that we look along the thickness, so there is different kinds of possibilities that one can have a redistribution of the charges there. Particularly, one can again input some dopants into this particular regions there. So that we'll try to understand today, like how one can have a proper redistribution of dopants at the interface level. Okay, this is what we have seen in our last lecture, and I think we stopped here at this particular part here. So from this, we'll start to understand a very important part, which is called as oxide charges. So this is an important part, because whenever you're growing in oxide layers, uh, there is a formation of oxide charges either at the oxide layer or at the interfaces. So that is going to affect your device performance. So it is necessary that one has to have a proper idea about oxide charges. Also, one has to have an understanding of these oxide charges. So we'll try to discuss about this particular part today. Okay, so in VLSI, when we are talking about this VLSI, the thin oxide layers, okay, of say 20 to 200 angstroms are very much in demand, because that is where mostly or usually the thin oxide growth processes are taking place. Secondly, we have discussed about this dry and wet oxidation processes. So most of the times when you're trying to grow very thin layers, so it is essential that a controlled growth has to take place. Rather, I would say that the growth with respect to the oxide charges are necessary to understand for us. Okay, so what we'll do, we'll try to understand what are these particular oxide charges. So most of the times this, when I'll just move further. Okay, so you can just look upon this part. Okay, most of the times what happens when you are thermally oxidizing the silicon surfaces, then in that particular case, what happens is that there are different oxide charges along the surface and the interface of silicon and silicon dioxide. So there exists this transition region, and along this transition region, you can find such charges. So yeah, this charge I'll just use pointer. Yeah, so these charges can be found along the surfaces and the interfaces. Okay, uh, most of the times what happens is that these charges, they induce some opposite polarities in the silicon substrate. Now note down that this is a very important part, because if there is some opposite polarity coming into picture, that is going to affect the total device. I mean the output of that device or the characteristics of that device. So whenever, let's say, we are trying to fabricate a MOS device, at this particular interface, if you try to see that the polarity is totally changed, it is going to affect the device, I mean MOS device performance. So it is necessary that one has to understand this particular part. It is very, very essential in case of fabrication of oxide layers on the silicon surfaces. So what are these different oxide charges? So just you can see that what is happening here. So you have this silicon substrate, we have grown silicon dioxide, there is a transition region, and now you can see that along this whole thickness, you have different oxide charges being present. Okay, so one can say that you have QM. So I have just mentioned all these charges here. So there are different charges. Let's say you have interface trapped charge, okay, which is QIT, which is shown here. So I'll come to the details of that particular charge here. Okay, this is located at the silicon dioxide interface. You have fixed oxide charges. So this is positive charge located within 3 nanometers of silicon dioxide interface. So almost you can see that along this thickness and up to 3 nanometers, you can get this different charges, the oxide charges, I mean, and they are referred to as the fixed oxide charges. You have another charge which is called as oxide trap charges. These are associated with the defects in the silicon dioxide. So where do you get this? So along the silicon dioxide, so we have already mentioned that you have silicon dioxide here, you have silicon here, in between you have SiOx. So that means the X or the subscript X for the oxide O has this kind of an points present into it. Okay, you have mobile ionic charges which is called as QM, and that is just a result of the contaminations or the dopants. It can be either the contaminant that is been introduced while oxidation processes, or otherwise it can be due to the dopants that is been done after the oxidation processes. So these are the mobile charges. Okay, so the fixed oxide charge, that is QF. Here I'm talking about this particular charge, which is QF is this one along 3 nanometers. Okay, usually we call it as a positive charge. Okay, this cannot be charged or discharged. It is not allowed beyond say 3 nanometers or say 30 angstroms here along the interface of silicon dioxide interface. Okay, so usually you will find this. So whenever you have this oxidation layer performed on the silicon, most of the times at the interface you will get such kind of an fixed oxide charges. Okay, so one has to look into this particular part. So depending on the oxidation and the annealing conditions, its density ranges from, so most of the time the density will, it ranges from 10 to the power of 10 centimeter, I mean per centimeter square. Sorry, it should be per centimeter square. So it is 10 to the power of 10 per centimeter square, or it can be up to 10 to the power of 12 per centimeter square. See, note down that this particular fixed charges at the interface, they are having a density of, let's say, 10 to the power of 10 or 10 to the power of 12 per centimeter square. Okay, so quite significant charges, oxide charges are developed at the interface. They are certainly going to affect the performance. Okay, of course there are ways to remove this, so we'll discuss in subsequent parts of our lecture here. In case of your mobile charges, so we are talking about this mobile charges. I just mentioned that this is because of the contamination. So whenever, sometimes what happens, whenever you are trying to thermally oxidize the silicon layer, and let's say that by some ways you already had done previous oxidation using some different kind of uh, gases, then what happens in the chamber, if you don't purge out all the gases outside, still along the walls of the chamber there can be some adsorption process taking place. Now what happens, when you put your silicon wafer inside and start doing thermal oxidation process, then this contaminants at certain temperatures get activated, and they might move inside this layers here. Okay, so most of the times, or whenever you do one kind of an oxidation process or some thermal processes, you have to clean up the chamber thoroughly so that no contaminant are present in the chambers. Okay, if at all there remains any contaminant, then they are going to play a very significant role because they form the mobile ion charges within the layers here. This is one part. The other part is what? The other part is purposefully you are trying to input the contaminants into the surfaces. Now that particular part we call it as an ion implantation processes. So you can go and put an ion forcefully into these layers. Now that ion can possibly form a mobile ion charges there. Okay, so that is how the mobile ion charges are being considered. Again, most of the times these mobile ion charges are considered to be positive. Okay, so I have just shown it like sodium potassium ions. So if at all these alkaline ions they are present, okay, they form a mobile ionic charges, and they will contribute towards the total IV characteristics of the device here. Mm. Okay, what about this? So the density, if we try to discuss about the densities, they are again in the same range of 10 to the power of 10 to 10 to the power of 12 per centimeter square. Okay, of course, I'll come to this part laterly. There is one consideration of ionic radii. So it's not that every ion, which is, I mean, the contaminant ion which is moving into the silicon dioxide, can move into the surfaces, okay, or into the matrix of that silicon dioxide. The reason is the compatibility of the ionic radii. So I'll talk laterally on this particular part. Okay, we talked about these trapped surfaces now. Okay, I mean charges, the trapped charges. These are again positive or negative, so depends how the traps are being formed. Okay, so we have discussed. I mean, whenever you have talked about semiconductors. So in case of semiconductors, we talked about trap states. Okay, so these trap states are being particularly induced because of some defects, right? So we talk when there are some defects, then there are some trap states that are present. And usually these trap states, they can have confinement of the electron in the states there. So again, when you are talking about trap charges here, they have similar kind of a role to be played here at this particular transition regions. Okay, and that's why whenever this particular trap states are formed, they contribute towards the avalanche processes. Okay, might be you have discussed this in the semiconductor physics part. So what are these avalanche processes and all? And most of the time, these high currents can be possible. I mean, leakage currents that are being induced, that can be through the trap states here. So that is one of the possibility, and hence this interface where you have these trap charges, they have to be recognized initially, and then a suitable processes has to be done so that you can control these charge states. Okay, this is very important part here. Okay, otherwise they are going to significantly affect the current, the resistance part of this particular device here. Okay, if most of the times okay, when I'm talking about all these charges, okay, when I'm talking about all these charges, one has a question in mind. Okay, how we can determine these charges? So there is a very simple technique. We called it as a capacitance voltage analysis technique. Maybe some of you might have used this earlier whenever you are teaching semiconductor physics or another course related to that. So this capacitance voltage charge is very important. See, what is happening is at the interface or these surfaces, you can see that there are the charges that are getting accumulated. So naturally, they are producing some capacitance over the whole region here. So if I can calculate the capacitance of the whole region, naturally I can get a very good gradient along this region or along the thickness with respect to the voltage, and one can understand this all traps charges. So whatever the trap charges are present, that can be easily determined because along this whole region, say silicon region, the capacitance will be different. Along the transition region, the capacitance will be different, and along the whole oxide layer, there will be a different capacitance available. So one can have a very good mapping of this analysis through capacitance voltage studies. Okay, there are now we can get earlier we used to get only the spectrum of it. Now we are using different cosmol and different kinds of softwares. One can also understand these states, so one can simulate this whole region to understand the capacitance that is developed throughout the thickness here. Okay, now what is happening there? We talked about this, right? We also were discussing in our last lecture. See, what is happening? You have a silicon surface. Let's say this silicon is crystalline. Okay, just for an our assumption, I can say that we are assuming that this is a silicon which is an crystalline. We are growing on silicon oxide. So what we expect is that along the lattice, the silicon has to grow. So whole the region from the silicon to silicon dioxide, it has to be an epitaxial growth now. Okay, that doesn't happen. The reason is that the transition region, sometimes there is a break because of the transition region, and then you will not get the same crystallinity following the whole silicon dioxide layer. Now that is where you will have stress and strain components coming into picture. Okay, so that's how it is going to happen. So just you can see that through the transition. So let's say that this is where we are discussing this silicon layer. Let me talk it as a crystalline layer. So it's very well periodic in nature. So throughout the crystallinity is maintained. Either I go the vertical or the horizontal lines, I can see that the silicon is very well crystalline in nature. We have grown and silicon dioxide onto it. Okay, so I was expecting that when I'm growing the silicon dioxide on the silicon surface, the crystallinity should follow the same structure. So I should get the same hexagon kind of a structure, which has to grow over this particular layer. Okay, so what happens, let's say while growing process, I mean the diffusion and the reaction processes at the interface, if at all there has some break or the bondings are not properly formed here, what will happen? The crystallinity will break here. And now once the crystallinity is broken here, naturally over the whole thickness range, you won't get the crystallinity again. So that means the epitaxy of this particular silicon cannot be maintained throughout the silicon dioxide layer. And that is where we have to have a proper understanding of this. Now you can see I already mentioned here something. So this is QF. Now this is what, this is a QF. QF is what we were talking about, the fixed oxide charges. What has happened, because there is a break or the bonds are not properly formed, when the silicon dioxide is grown on silicon surface, you get a charge, the silicon plus mentioned here, and this particular silicon plus is nothing but your fixed oxide charges. This is how the fixed oxide charges are developed. This is how one can say that the charge oxide, I mean trapped oxide charges are developed along this particular region. Okay, so we need to understand this part. I was talking about the epitaxy, right? I was just mentioning about the epitaxy. So along the silicon dioxide is growing. If at all it follows the same crystallinity, it will have a very good epitaxial growth of silicon dioxide on the silicon surfaces. Okay, but let's say it does not happen, and this is what is happening here. Again, a very important part comes into picture. That is the defects. We can see here clearly, we can see there are defects being formed. Because of these defects, you have stacking faults coming into picture, and this stacking faults will make a very, I mean they will play a very significant role in your output characteristics. Why we are discussing this? Because in the later part, when I'm going to discuss about the ion implantation, this is a very important part coming into picture for us. So initially, if we try to understand this, the later part becomes more easier for us. Okay. Normally what happens, see, I just mentioned here that low temperatures, let's say you have an hydrogen that was purged during the oxidation processes. Okay, so this is where we talked about the this is where we talked about the uh, forming gases. We call it as a forming gas, a mixture of hydrogen and nitrogen. So this is the ratio in which these particular gases are inputted into the oxidation processes. So what happens is that in this particular processes, one can one can neutralize this kind of charges that are present. Okay, so if at all I have to have a control of this particular whatever we are discussing about the oxide charges, then there has to be some technique, right? There has to be some technique to get rid of this particular oxide charges. What is that technique? So I just mentioned here. So whenever the oxidation is taking place, one can have a proper mixture of gases that can be inputted into the oxidation process. Now these are the inert gases. They are not going to have any kind of an interaction within these layers here. Of course they will just help the oxidation or the diffusion or the reaction process to occur easily. Now note down, I have mentioned here that, see, at low temperatures, let's say that you have already finished your oxidation process, you have analyzed the oxidation process, I mean, you have analyzed all this total device, and you came to know, using, of course, using, I just mentioned, like capacitors and voltage studies, and you came to know that there are so many oxide charges that are being present. Now I want to remove this. Again, I want to change the amorphous, and I have to change it into the crystallinity. So this is the process. At low temperatures, you can put some forming gases into the sample surfaces, and then you can neutralize this particular oxide charges that are present. So that is a very easiest and simplest process that has been followed in fabrication of, I mean, in VLSI fabrication processes. So one can have this control now, and one can reduce the different kinds of uh, oxide charges that are being developed during oxidation processes. Okay, this is what the same thing. Like initially, we have this substrate, silicon substrates. We do the oxidation processes, and now once the oxidation process is done, if you take this particular samples, try to study the whole capacitance voltage studies, and you analyze that, okay, the process of oxidation done is quite well. No problem. I can take this process to a further step now. If at all you find some such kind of an defects or such kind of oxide charges being present in the sample surface or the interface, then one can again go back, put the samples, use this forming gas, input it into the system, have a low temperature process now, particularly annealing processes, so that you can neutralize this particular interface trapped charges. Okay, so that is one of the ways one can do this. Okay. Okay, so this is what happens. So during the oxidation, I just mentioned that the defects are being induced. Due to defects, there is a possibility of having dislocation, stacking faults. Now, whenever you have this dislocation or stacking faults, okay, so what happens is that there should be some changes in the structure. Okay, particularly what happens is the volume expansion takes place. Okay, of course there can be linear expansions, there can be surface expansions, there can be volume expansions. If you are talking about the 3D structures, we particularly deal with the volume expansion processes. So that is quite naturally been seen. Okay, again, this particular encapsulation of your contaminants can create defects. Okay, again, this is the process. So whenever we talk about oxidation, that is what the encapsulation is done. But then this encapsulation can again have a creation of defects in the surface or at the interfaces. We also mentioned that, okay, because of the defects that are induced now at the interface or the surfaces, you can have stress strain being developed. Okay, so one has to remove or have a good control over this particular stress and strain. Okay, particularly when we are talking about defect densities. Okay, so these defect densities naturally has to be dependent on your oxidation rate or temperature. So if I can understand properly what is the oxidation rate for a particular thickness that has to be grown on the silicon surface, as well as if I can understand what is the temperature that is essential whenever the oxidation takes place, there can be lesser number of defect densities, then I can have a proper optimization of my device. So that is how one can see. Okay, and hence using all these processes and different kinds of processes, I mean the post processes I'm talking, if you can get the total study available, one can have a very good control, as well as one can reduce the defects or the impact of defect on your devices. Okay, uh, okay, so I think this is what I have to discuss about the different oxidation charges that are being taking place along the interface and surfaces. Okay, there is another process. So industrial processes. So there is another process where one can have an oxidation taking place on the silicon surface. This is called as the anodization process. There is another one which is called as a plasma oxidation process. So we already discussed about the uh, furnace oxidation processes. We talked about the rapid thermal oxidation processes. We discussed about different wet dry processes. Apart from this, we will have this particular anodic oxidation or plasmonic or plasma oxidation processes. Okay, this is the technique that is been shown. Mostly this is an electrochemical process here. One can see that. So here you can have an anode where you can use your silicon substrate here. You can have an counter electrode which is called as a cathode here. Now this can be platinum or a graphite, that is possible here. You can put some electrolyte. So particularly when you have to do some oxidation processes, most of the times one can have an KOH electrolyte, NaOH electrolyte, H2O electrolyte. So different kinds of electrolytes are possible here. So what happens is along the silicon, one can have a very good growth of hydroxide taking place. So note down that most of the times what happens in this case or anodization processes, one can get a mixture of oxide and hydroxide layers. And later on, again, you can have a controlled process of thermal oxidation, and then you can and remove the hydroxide present on the interfaces or the surfaces. Okay, mostly this process is not very well used in the fab, I mean VLSI techniques. Okay, this is very rude process, I can say. The control of the oxide layer or the hydroxide layer depends on the voltage here. Okay, so one has to have a very good control over the voltage as well as the potentials that are being taking place within the two electrodes and the electrolyte. So that is where you have to have a good control. Secondly, since this process is through the application of an applied voltage, so the ions that will be moving through this particular electrolyte towards the respective electrodes. So let's say that I have H plus here and OH minus here inside. If I have put the silicon at the positive end here, so naturally the OH minus will be attracted towards the positive electrode here. The H plus will be attracted towards the negative electrode here. So what happens? The OH will be formed at the surface here. So they are being forcefully been uh, allowed to move towards the semiconductor or the silicon surface here. Okay. So in that case, what happens is that if you cannot control the voltage properly, then naturally whole of the OH minus will suddenly come and gradually they will form Helmholtz layers here, and slowly you will have a hydroxide or an oxide layer which is uncontrolled. Okay, so that's why this anodic oxidation process is not very well utilized in the fab processes. Okay, this is just for your understanding that there is another process where one can go and do some oxidation on the silicon or any other semiconductors using anodic processes. Okay, this is called an anodic process. There is also another term called as cathodic processes where one can grow metals. Okay, so that is the opposite case of anodic oxidation process. The plasma oxidation is what? See, you can see here a very high voltage is applied. Now this is applied between a cathode and an anode here. Okay, and in between you have an high frequency oscillators that are being utilized. Now what happens is that this will produce an quasi gas in between this particular chamber here. One can put the silicon sample here. Okay, so what happens because of the plasma plumes that are being developed at this particular region here, they will start to oxidize the surface here. Okay, so this can be possible through different kinds of gases that can be inputted through the flow meters here, I mean mass flow meters here. So one can input the oxygen or some inert gases through this particular inputs, and then they can move inside. here you can have the gas getting ionized. So you have an ionized gas and some electrons. These are the quasi states which we particularly called as a plasma state, and this plasma state will be helpful for us in oxidizing the surface. Okay, so again in this case, you can see that a silicon cathode is being utilized here. In this case, what happens is that although this is a very good technique, okay, this is limited. This is limited by the dimensions of this particular apparatus. Okay, so you cannot have a bigger apparatus for this, because most of the times the plasma is being done at a very narrow distances or area. Okay, so that means your chamber has to be smaller in that case. And sorry, and if a chamber is smaller, naturally your silicon wafer that is been inputted here, that has to be following the chamber, I mean the dimensions of that chamber. So naturally this is not very commercially been utilized. Of course, whenever you want to remove some surfaces, I mean you want to etch out some surfaces, this technique is very much useful. So the plasma etching is a very important technique. Okay, so either you have an plasma oxidation process that can be taking place through this particular method, or else one can have a very good etching of the surface using plasma techniques here. Okay, so the same apparatus can be utilized, so depending on the output that you are looking for. Either you are looking for an etchant, I mean etching the surface, or you are looking for oxidation of the surface. So these two processes are very important in that case. Okay, okay, just very quickly, so you already have understood that an anodization process, where you have a positive electrode, you have a negative electrode. Okay, which through these electrodes one can put some I mean apply some voltages. Now the solution has that particular ions inside, so forcefully one can make the ions to move towards the respective electrodes. Okay, a positive ion will go toward the negative electrode, a negative ion will go to the positive electrodes. So this is how one can again have the oxidation process. So silicon surface can be oxidized to silicon dioxide using electrochemical processes, particularly anodization processes here. Okay, okay, let me go through very quickly to a new topic, where we are trying to understand that, okay, we had a thermal oxidation process on the silicon surface. Okay, so this was a thermal processes where we discussed about what happens at the surface of the silicon. There will be an interaction of the oxygen. The oxygen will move inside the silicon surface, and it once move inside the silicon surface, that is where the diffusion starts. A chemical reaction takes place and you get an silicon dioxide out of it. Okay, so that is what one of the processes where you have such kind of an diffusion. So using this process, one can again input some dopants into the silicon substrate. Okay, see, please don't get confused between two different processes I mentioned here. Okay, I just mentioned one process where you are talking about the silicon oxidation. So in that process, what I mentioned is that, okay, the silicon surface is there, you have an oxygen which was inputted, that oxygen moves towards the silicon surface. Okay, and so I was just mentioning that, okay, this is the silicon surface, you have an oxygen that was moving inside now. Okay, and now what is happening at this particular surface, this oxygen is moving inside. Okay, so what happens, it starts to interact with the silicon surface, it moves inside now. Okay, once it moves inside, it will start to have an reaction with the silicon now, so as to form silicon dioxide here. Okay, so now The first process is an interaction process. The second process is a diffusion process, wherein the actual bondings will take place to have an silicon dioxide. Okay, let us say that if at all I have this silicon surface here, and let me say that I want some boron to input into this particular case. Okay, so instead of oxygen, if I try to use boron and I try to use the same process of thermal diffusion, what will happen? This boron will come to the surface of silicon, start interacting. It will move into the bulk part of this silicon. The boron will try to interact with the silicon now. Okay, so if I have a control process, no problem. I might have something called as silicon borate been formed there. Okay, I'll not go to the balancing of this particular case. Or else if I don't go for a controlled diffusion process, maybe I can have some defects present wherein the silicon will be replaced by the boron. There is a possibility of this also. Once you have a controlled process, the other way you don't have a control process. Again, I mentioned that when you don't have a control process, there is a possibility of breaking of bonds taking place, the defects being induced into the system. These defects can be later on be filled up by the external elements that are moving into the surface. What I mean is here that I can have the doping process through the diffusion. I can have the doping process through this particular diffusion, the thermal diffusion process I am talking about. Okay. Or else I have this another process now, which is called as ion implantation process. Okay. Wherein you have an energetic ion beams that are injected. So you can have different kinds of ions. Okay. So maybe this is you have an say, just for an example, some gold. You can also have some silver. You can have phosphorus, arsenic, boron, oxygen, sulfur, different kinds of ions that can be high energetically incident on the silicon surface, and they are forcefully made to move inside the silicon matrix. So this particular two different processes are very important where you are trying to have a dopant being introduced into the silicon matrix. Now what we are trying to do is, let's say we were discussing about this part where we were talking about the silicon. We have made another structure that is silicon dioxide onto it. Okay, so let's say that we, by some means, I have each this particular part. So now the channel is open for me. And now I want to introduce some dopant in this region here. So this particular region, I am trying to see that I want some dopant here. So that I may have, say, this is where I have a silicon now. I have a silicon here and I want some dopant here such that I want to either go for N or P type region. So this particular process where I am trying to open a channel and then inputting some dopant into it, that can be done through two different processes. One is called the diffusion process or the ion implantation process. Most of the times, diffusion process leads to more defect formations into this particular region, and hence to have a proper channel with the controlled dimensions and the controlled region, one can go for localized doping processes that is called as ion implantation. Okay, so that's why we will try to understand now what is a doping, how a doping is taking place, and how one can move forward for this particular cases. Okay. Okay, so I just mentioned here to control the majority charge carriers type. So I am trying to have a dopant here in this particular region. That is why I want to have a change in the type. I mean, change in the carrier types. So either P type or N type. So if N type majority carriers, I know that this is electrons. P type, it is holes. Okay, so I want to have a controlled change in this particular region here. Okay, or else I want to have a resistive layer here. Okay, so both ways is possible now. Okay, so that means the further steps we are moving inside now. Okay, the first step was silicon, how we tried to get the silicon wafer, wherein we tried to make the dyes out of the silicon wafer. The second step, we went into the silicon dioxide processes. So we talked about the thermal oxidation processes. Now what we are trying to do is, now we have to make a proper channel. Okay, the channels where we can change the conductivity or change the type of that particular region here. And this can be done by thermal diffusion processes, which we have already discussed for the oxidation processes. And another process which is called as ion implantation. Now that is where we are very much focused and very much interested in. We'll talk about this in more details about the ion implantation process. I have already mentioned why we require this process, like why we want to have a doping. Just we want to have some formations. So we are going to later on, like when we complete all the steps, all the processes, we are actually going to see that how a MOS device will be formed, how a bipolar transistors can be formed, how a PN junction can be formed, how you can go and devise different kinds of ICs. What are the layouts that we'll be trying to understand, right? So naturally, now in this third step, we are going into the doping processes. Why I require? Because I want to make some PN junctions out of it. I want to change the conductivity. I want to change the resistivity. I want to change the region, either N type, P type, whatever. I want to go for a source formation. I want to go for a drain formation, a gate formation. So whatever that, I need some kind of a doping at that particular region. Okay. So we are not going to dope throughout the whole regions. Okay, if there is a necessity, we will dope for the whole region. If there is a requirement for a certain region, we'll have a proper channeling process, and then through the channeling process we can go to make some doping in that particular regions. Okay, we will try to alter this particular conductivity. We can form this particular, what I have already mentioned, different kinds of bases, emitters, resistors, drains, capacitors, whatever we want, we can do that. We can again go and have, let's say that the crystallinity of silicon, or we go for a polysilicon, this can again be doped there. Okay, so just let me have a very quick understanding of this diffusion process or an ion implantation process. Okay, so if I am trying to discuss about the diffusion temperature, sorry, diffusion doping processes, naturally you can say that you need to have this diffusion processes at high temperature. See, low temperatures, the diffusion cannot be taking place because you have to break the matrix, and that matrix can be break only at high temperatures. Now what happens at high temperatures? You are going towards the melting point of that silicon, and thereby you are trying to break the bonds. Now this is where you can again break the bonds and input some external dopant into it, right? So that is where the diffusion process comes into picture, and this has to happen at certain high temperatures. It cannot happen at low temperatures. So most of the times the diffusion process takes place at high temperatures. The other point is that this is where the profile, if you try to see the diffusion will be, profile will be, let's say we have opened this channel and you start thermal diffusion processes in this particular, say, what will happen? The diffusion will start in this way, right? It will start, it will start, it will start. So what happens is that this particular case will have a diffusion process isotropically in the direction or in one direction only. Okay, so that is what makes it a unidirectional, I can say, a unidirectional dopant profile that can be possibly done through the diffusion processes. It cannot be independently controlled. I mean, the dopant concentration or the junction depth. The uniform cannot be possible because you are using a high temperature and then diffusion processes that is taking place. It will certainly have a temperature gradient throughout. So at this particular part, let's say, or let's say this particular part, if I have a heater arrangement done here, so it will go in this direction. If I make the thermal diffusion happen through this particular, I mean the gases are being allowed to move in this direction, what will happen then? This control will be having a different temperature gradients throughout. A high temperature will be here and low temperatures will be here, and accordingly the total region will be having a gradient where the dopant concentration or the junction depth is not possible here. Okay, okay, that is what been seen here in this particular case here. Okay, any message?
Sir, Srinivasan here, sir.
Yeah, yeah,
Sir,
please, please, please.
this diffusion you're talking is about um, hmm, will the temperature required for liquid to liquid diffusion also, sir?
Liquid to liquid means?
Uh, Two liquid or gases, uh, gases we want to diffuse. One gas with
No, no,
another
no, no,
gas, or one gas with a liquid we want to diffuse means
no,
do the
no, 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 sir. No, no, no. Now, see, this is a different process we are discussing. See, earlier we were talking about that wet process and dry processes, right? So that is where we were trying to develop this particular oxide layer here.
yes, sir.
Okay. Now we are not talking about this particular layers now. Now what we are trying to do is we are having a channel now, and now we want to have a different kind of conductivity available for me, either n type, p type. I want to make something a different
Okay.
region here. Okay,
Okay.
so in
Okay.
that case I am talking the diffusion process now.
Okay.
Now I talked about thermal diffusion process. So what is happening here? See, let's say that this particular device now, which is having silicon dioxide here, this is an protective layer now. Okay, this is a silicon wafer, this is an open layer now. So this particular sample is inputted into a chamber now. So what happens? The gas is coming now. Okay. So now the gas is either of the dopants. Okay. So let's say the boron I want. So what I'll do is the ionic boron, I'll try to input it into the sample through the chambers here. So that boron will try to come here. Okay. So note down that this whole sample is at a very high temperatures. The reason is that the silicon has to be easily made in such a way that the boron can move inside the silicon matrix. That can happen, yeah, that can happen only when you have a temperature wherein you can break the bonds of silicon, which means that a melting point. Okay, this is where one process is possible, wherein you are trying to have a heater arrangement here so that you are trying to use a melting process here. The other way is that the thermal energy is given to your gas molecules. Now, note down this is either boron, phosphorus, arsenic, whatever the dopant that you want, and that will move inside this particular region here. So, using the thermal energy, they will move inside and get diffused. Sorry? No, 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 no. I am at the same slide. So that cursor is, you can see the cursor, right?
Yes,
Yes,
No?
sir.
small point is there, sir. Yeah,
Ah,
pointer.
yeah, yeah. Small point is there, right? Yeah.
Yes, sir.
So
Yeah.
this is what you can see.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Cursor is shown. Cursor is shown.
Yeah. So that's what, like I was just mentioning. Okay, see, again I am trying to explain this part if it is not understood. यहाँ पे क्या हो रहा है? I mean, okay, sorry, I'll just go with in English. Okay, so this is a sample, right? Now, what we have done, the first step was this one. We made silicon. Okay, so we have already done through discussed about this ingots. We made ingots, then we cut into wafers, and then die. We have made this. Second step was our silicon dioxide, right? So the thermal processes that we used, where oxygen was inputted, and then we had this oxidation layer been done on this silicon wafer. This is the second process. Okay, first process completed, second process completed. Now we have done some selective